Hello, everyone. Happy Thursday. It's great to see so many people here. My name's Keith Edwards. I'm the director of the GVU Center, for those of you who haven't met yet. I'm really happy to see so many people at today's talk. So before I turn it over to today's speaker, a few administrative announcements. First off, if you have devices that buzz or beep or vibrate or make annoying noises, now would be a good time to turn those off, please, so we don't distract the speaker. Second, if you're taking the course associated with the brown bag, the sign-up sheet is over here on this podium, so please just make sure you sign that before you leave. And finally, please be sure you clean up and throw away all your trash and recycling and whatnot as you leave this room. We don't have the resources to go and clean up after you. Thank you. So next week's speaker, I'm happy to announce, will be William Pike, who will be visiting us from Pacific Northwest National Labs, who will be giving a talk on interactive analytics. I thought next week. Maybe I'm wrong. Alex will correct me. If I'm wrong, pay attention to the emails and they'll have the details. But today I'm happy to turn it over to our very own Alex Endert. I think a lot of you have probably already met and know Alex. He's a fairly new assistant professor here at Georgia Tech who does visual analytics and really needs no further introduction from me. So I will turn it over to Alex. Welcome.
Awesome. Thank you. Thank you. Okay, so I've got a bunch of stuff on my shirt here. Is everything working? I think the mic is working, and this other thing? Perfect. All right, good. And I also have a tendency to wander, because I don't exactly know where the middle of this room is, but I'll just stand over here for a while. So yeah, this is a real pleasure actually to be able to talk to you all. In putting together this talk, I thought about what it is I actually wanted to say, and I thought I'd sort of share this idea about interactive visual affordances as part of this talk, and to use it as an opportunity to see how well it goes over, and if I'm able to convince all of you that this is a fun idea, or at least as fun as I think it is. So my goals for this talk are really these three things, 3.5 sort of, to share this idea that's interesting to the students and I that work on it, motivate that idea with some prior, current, and some future ongoing work, and hopefully stimulate some interesting discussion and collaboration, and if nothing else, give you some interesting visualization videos to look at while you all eat, and we'll go from there. So, interactive visual affordances. I think a good thing to talk about, first of all, is this idea of affordances and really where this idea is grounded. And affordances have been around for a while, at least the theory of them, since 1977 and perhaps even earlier than that, where James Gibson sort of thought about affordances as objects in the physical world that afford some opportunity for action. Right? These are oftentimes given the examples of cups that have handles, and those afford you to hold them and tip them in certain ways. Tools that have handles and that can be used for specific things, so hammers afford the ability for you to do something with them. And what we do with them are oftentimes a result of our experiences in the world. They are they are based on things like perception of vision, but also context and situations, and we plan our actions with them based on our experiences as human beings. And we develop these over time, and we learn by example and other things, but really they are based on our experiences and so on. And so then, my area more so of information visualization is really this interesting field about binding data values to graphical encodings. Right? We ultimately, what we do is we illuminate pixels in certain ways that actually represent the data and help us think about our data in specific contexts, for specific tasks, and then ultimately foster this analytic discourse with specific kinds of data. And when I say data, I mean things that range from text to tweets to videos to images to network packets, cars, anything that can be represented digitally, oftentimes through the use of like a spreadsheet or other kinds of common metaphors like that. And these then foster these cognitive processes like discovery and sense-making, and really these deeper concepts that can help explain what it is that happens when we analyze and think about data. And so to walk through some of these examples, this is sort of a standard information visualization technique, as we call them. It's a stacked bar chart. The particular data here is server usage on a server, where each color depicts a different kind of service running on a server over time, and then you have total usage as the stack, or the height of the stack. So the graphical primitives, if you will, that we're using here are things like the length or the height of a bar and the color that we use to actually encode the type of, or the category of the service. Well, as we start to add interaction or user interaction, which is an area that's particularly interesting to me as well as others, we oftentimes see it done by these types of graphical user interfaces, which afford direct manipulation on very specific data attributes. As you can see here, for example, a slider that you can slide and select the time range that you're interested in, checkboxes where you can select certain types of or categories of server or services, and then you see the result as a new visualization or updated visualization to really help foster that exploratory data analysis that we, as visualization researchers, really appreciate and try to support. And we've gone through model this user interaction in a pipeline that looks very similar to this. And you'll see different renditions of this. It came from Ben Schneiderman's sort of direct manipulation and has been modeled by others such as Stu Card as this type of a model here, where what you have is you start with data sources, which then turn into data tables, visual abstractions, ultimately views, and then you have this user at the end that is a recipient of those views, but can act upon things like changing the type of data transformation, change the type of visual mapping. So for example, I want to map a certain kind of value to a height of a bar, which makes bar charts, or it might be the distance between things, which might be in Cartesian space, such as scatter plots, and ultimately change the types of view transformations that I do to go from, for example, a scatter plot to a bar chart to a pie chart, and so on and so forth. And I'm using these examples, but you can assume that, and there are many other more complex visualizations as well. And the key here, and you'll see this going forward, is that these afford direct, explicit control over these kinds of parameters. So over the parameters of what kinds of data transformations, what kinds of visual mappings, what kinds of view transformations. And so, visual analytics is a somewhat newer field, and a key difference that visual analytics has to information visualization is it incorporates a lot of data analytic models. And so, for example, one of those is dimension reduction models, like here. Who here knows what principal component analysis is? Fair amount of you. So what it does, try to explain this as simple as possible. If you think about three-dimensional data points floating in space, right? You have a cloud of points in front of you, and you have a flashlight. And you can shine that flashlight at different distances and different angles into that cloud of points. The shadow that it casts on the table, for example, that is what principal component analysis projects, right? And so what you see here in this A space is points where the similarity is encoded by the distance between any 2 points. So you can assume that points that are closer together are more similar as determined by principal component analysis. And so what we've done in this particular example here, and in visual analytics in general, is we've adopted user interaction designs or metaphors that were intended originally for information visualization for visual analytics. So you see the same kind of control panels, the same kind of interfaces, buttons, sliders, so on. However, a key difference, and this is an important difference, is that the interactions are now on model parameters as opposed to data attributes and data parameters. So for example, the checkboxes are no longer to select and unselect which kind of server attributes that you're actually interested in, but they are actually to select which principal components of a principal component analysis you would like to include in your dimension reduction model, right? And as somebody, just taking a quick straw poll here of who's familiar with this, this actually raises fundamental usability concerns because not as many people are familiar with which services of a server you're actually wanting to visualize as they are which principal components you would like to include and by how much you would like to weight them and how you'd like to combine them, or maybe you want to use multidimensional scaling as opposed to principal component analysis, and you see how this complexity quickly increases and creates this interesting opportunity. this opportunity of, maybe it is time to consider a new model or new models for user interaction for visual analytics in particular, right? Moving beyond this direct manipulation sort of WIMP interface that has been sort of transformed and adopted over the years. And the approach that I'm going to share today and give some examples of is really how do we enable people to act directly on the graphical encodings. So we said the height of a bar, the distance between points, the color of the bar that we actually encode. How do we sort of let people interact directly on those as opposed to these control panels and so on. And so this is really this idea of interactive visual affordances, right? The ability for humans to plan and execute on that plan or act on hypotheses and questions about their data by directly manipulating these interactive visual primitives, right? Color, length, distance, so on and so forth. So to illustrate this a little bit better, typically what we have with direct manipulation is we assume that people act in these red boxes on these control panels, and that produces an updated visualization. Right? And what I'm advocating for, or thinking about, is how do we turn that around? How do we let people interact in the visual space, and the system can infer the parameterization of these models, and if you want it to, move the sliders for you, right? That's a simple way to describe what is going on. And I'll walk through a few examples of how we've done this to try to motivate this idea a little bit better. One of them is literally taking this tool, which was called IPCA, and flipping exactly that around, right? So you take this box in red here, which is this, we oftentimes call it lower dimensional space or two-dimensional space of the data points. We say, how do we let people move the points around directly, right? So I see 2 points that have a certain distance from each other, and I, given the domain expert of the data that I see, whatever data that might be, say, those should be further away. Right? They are less similar than what this model, this computational model, thinks that they are. And we do that, getting slightly technical here, by computing either the parallel residual eigenvector or the orthogonal residual eigenvector based on that updated distance. Right? And I won't get into any more technical details. They're in this paper. If you are interested, please come talk to me and I'm happy to share that. But it's really about the interaction design that we've gone for here of saying we want to let people move these points apart and have the system actually go through that computation, that effort, if you will, of solving for what these combinations are that I should be doing, what the weights of them are, so on and so forth. And we can basically convey similarity and dissimilarity in that kind of a way. We've applied that very basic generic concept of moving points further away and closer together to visual text analysis. We call this semantic interaction, but it's a similar kind of interaction design where we said when people analyze text, what are the interactions that they typically do, right? You have a highlighter in your hand, you might highlight things. You might pile documents closer together that you think are more similar. Right? Think about a conference table with just paper scattered about. You might make notes on them. You're probably not going to think about how many topics of a topic model you might need, or what clustering algorithm you might use, or how many clusters in a k-means clustering thing you're actually going to choose. But instead, you're just going to do these things like moving documents around and highlighting, so on and so forth. So the challenge, again, the research challenge, is how do you map those interactions to the actual underlying computational model? And we'll just watch a quick video here of this prototype where we see, whoops, back. Plane. Right, where we see dots are documents in space, and we can make them larger. I'll wander over here a bit, and we can actually help the user group and organize all of these points in space, and each interaction actually trains the underlying model in some way to help organize this layout. So edges between nodes mean that those documents share some sort of words, and ultimately all of these interactions help the system organize this space for the user, right? So I've moved 2 documents closer right here, and as a result, the system infers why that might be and brings other similar documents nearby. And over the course of several minutes or hours or even days, depending on the size or complexity of the data set or the task, we start to see more and more sort of nuances or incrementally add formalism to the actual layout in such a way, as well as the model, right? Because they're both very closely connected. here's another example. Word clouds are pretty commonly used, right? We have, the general premise is that in a word cloud, you take a whole bunch of text documents, you figure out which words commonly or frequently occur in them, and use size to encode that frequency, right? So terms are larger if they occur more frequently in the actual data set that you're visualizing. And here what we've done is we've said, why don't we use the size of the word as well as the position, right, being closer to each other, as an encoding which we can directly manipulate. And how we infer that manipulation is actually through training a topic model as well as the layout of the actual system, right? Or sorry, the layout of the actual words determined by the topic model that we use. So here we have all of English Wikipedia visualized, right? So 4.some million documents. And we've used a hierarchical topic model to determine which words should belong with which other words, and then laid it out according to the similarity between the terms in a topic model. And what we allow people to do, instead of training the topic model directly, is actually make words bigger and smaller and move them closer and further away from each other, right? Very simple, graphical, interactive interactions. And as a result of that, we might see Victorian Football League and this former Australian rules footballer, and we take that term and we make it smaller, and as a result, we see less information regarding that term, and by making it larger, we actually see more information start to appear about that term. Then we see this Australian Football League and we go, what does that have to do with Victorian Football League? We move them closer together and now we see a snippet of the actual Wikipedia article that describes the similarity and differences, at least according to Wikipedia, between those two terms. Right, we can make it even bigger, and we see even more data come by. But this idea that you're actually training the hierarchy of your topic model, as well as the topic model in general, based on these interactions that are purely in the visual. Right? You'll notice that all of these examples, there are no control panels anywhere. Now, in reality, what we might want is a balance of control panels as well as these types of interactions. But there is no direct control, direct manipulation over these parameters through control panels or other things in these types of interfaces. Right. Here's another quick example. You zoom out, you see all of these nice topics. You see a lot of things about sports and pop culture and other things. You might be more interested in India, so you actually grab that term, make it larger, and you start to see lots of other terms appear as a result of your interest in India that you've expressed to the system by making that term bigger. Okay, here is a more recent example. You'll actually hear a bit more about this during the Viz preview session later in, that's a later brown bag. This is a paper that was just recently accepted to our flagship conference, VAST, IEEE VAST, by Hannah Kim and some others, where she said, if we use, how do we let people move dots around in a scatter plot? Right? XY scatter plots are typically typically visualizations where you map a data attribute to the x-axis, to the y-axis, and you create a Cartesian space where each dot represents some value on the x and y-axis. And she said, how do we let people move points around in that space as a way to start grouping them, clustering them, organizing them, so on and so forth, and understand some differences between higher level ideas about the data. And I will do a live demo, so here goes nothing. Get out of that. Make this bigger. Good, okay. So here we have the system that she built. And each dot here is a car. Can you guys see that all right? I'll make this bigger. How's that? All right. Each dot is a car, and you have these green points on either side, on the low and high point of the axes, which allow you to drag points directly into them. So I might find a car that I like, right? This Porsche here, that's a nice car. I'm gonna drag that to the high side, and I find a car that I don't like, perhaps this one here, and I'm just picking these somewhat randomly here. But what I've done, what the system has done now, is actually compute the similarity and differences based on a linear combination of the data attributes between the car that I like and the car that I don't like, and map that directly to this axis. right? So this axis is no longer something like retail value or horsepower or some single attribute directly. It's actually this linear combination of these axes, where the cars that are more like this Porsche that I've put over here are actually on this side, right? So I see things like an Audi TT, I see things like a Subaru Impreza WRX, so on and so forth, and I actually see exactly why that is, right? The system has said, you are looking for things that have all-wheel drive, that are sports cars, that have a higher retail price, a higher retail cost, and those are more on this side. And the other ones are more over here, and they're things like, you know, other kinds of cars, and I can go in and incrementally tune this, right? I might see Mercedes over here, and I go, nah, that's a car I like, I'm gonna put it over there. And as a result, the system has updated this linear combination of the attributes, as well as the visualization up top directly. Similarly, you can go in, you can say, I actually don't care about the width of a car, and I take this bar and I drag it near the middle, near the point where it says 0, and again, you've updated this model directly. And here you see this interesting balance between, you likely will want some control panels that allow direct manipulation, but also this other sort of interactive affordance methodology for interacting with the visualization. All right, switching back. Okay. Looking ahead, this is where it gets a little interesting, right? What do we do now? And one of the things that came about was this idea of how do we evaluate the effectiveness of these interactive visual primitives, right? As a way to say, we have these graphical encodings that have different kinds of perceptual abilities, right? Or have been ranked based on their perceptual abilities. For example, how good is somebody at understanding the difference between two lengths of two bars versus two angles versus the size of two bubbles, so on and so forth. We actually, what we're doing is thinking about how we study how good people are at understanding the interactive difference between those. So how accurate is it for me to ask somebody to make a bar half as long or twice as long, or make an angle twice as big, half as big, so on and so forth, and whether those map up pretty well to the way that we simply perceive these graphical encodings, right? Because this is somewhat a fundamental question that we need to know if we think that this is a valuable way to go. Because our visualizations, if you thought about what we've been doing, are no longer these output-only views that we perceive, but we're actually thinking about how we put those as interaction mediums, if you will, and therefore understanding how effective these are for interaction is pretty important. So we're studying this, or we have studied this, over the summer. Results are coming, and so is the Chi deadline, so hopefully there's a results we'll get here before that. We actually tested this, right? We built some of these glyphs, some of these interactive visual primitives, as we call them, and asked people to do very low-level tasks, like make bars twice as big, 75% as big, so on and so forth, and looked at the difference that we get out of asking people to bend curvatures, or make bars taller, or make them smaller, or make circles bigger or shorter, or sorry, bigger and smaller, and so on and so forth. And you know, we were getting some interesting results that actually help us understand this interplay between interaction and perception when it comes to graphical encodings. Looking even a bit further, this is an interesting opportunity for us then to look into building a library of these, right? To allow people to integrate inherently interaction into their D3 or other web-based visualizations that they build. Right? Typically, a lot of our visualization libraries have been focused on how you allow people to bind visual encodings to data values and so on, as opposed to actually thinking about the interaction, which oftentimes was perhaps done in hindsight as control panels and so on and so forth. But here, with this library, which we intend to have at some point, we will allow people to do that more inherently and more directly as they design their actual user interactions and visualizations. And so, that is really short, but there you go. The work here, I'm really proud of a lot of the students that have done the work to make this happen. We are the Visual Analytics Lab. We're on the 3rd floor of TSRB, and I'd love for you all to come by and chat. And also, I suppose, if there's any questions, I'm happy to backtrack to some of the demos or talk about anything in a bit more detail if there's particular questions that you have. Thank you.
Time for questions? I think we have a few minutes for questions.
Yes.
So is it fair to say that you're doing supervised machine learning?
Yes, we're actually leveraging supervised machine learning into the user interactions that we're doing. And as a matter of fact, what we've come to realize is that this also has impact in the machine learning communities, and we're publishing in some of those, in the sense that it actually thinks about, typically when we do machine learning, we think about training based on data, but here we're actually, or training data, and here we're thinking about training based on user interaction. Where maybe the ground truth doesn't exist, therefore you don't have data to train on. And that's an interesting way to take this. John.
So in the system that Hannah built, when you took a Porsche on the one end and the other, that's a very binary yay, nay. Did you think about there's an axis there and I can put the car wherever on the axis that I want for how much I like it?
Yeah, so, right. We thought a little bit about that, but we started with trying to play with how do we represent that continuum, right? Where you say I have a car I don't like and I have a car that I do like, and then my axis is sort of this likability of a car axis. And things fall along that continuum in a linear fashion, right? Hence the linear combination of attributes. There are interesting mathematical formulations that actually look at nonlinear combinations of those, right? And how that might work. Now it was the binary one side or the other, not the it's sort of in the middle or it's 60% on that side. Those are interesting refinements, if you will, that might come in incrementally as we start to think about that. Yeah. Yeah.
So I don't know if this is possible with any of the systems you showed or not, but kind of naively I could think, the user might try to position stuff in such a way that there sort of is no possible solution. You set up a set of constraints against each other where it just doesn't make any sense. Is that possible here? And how do you convey information about that to the user if they're setting up a set of things for which there just is no solution possible?
Yeah. So if a user performs accidental or opposing actions, the system will try to learn from those. It learns from all of them. We usually leverage Bayes' law in some way to actually propagate changes over time, right? To say each interaction is not independent of any of the ones that are previous. And as a result of that, the system may come to a state that has conflicting information from the user. And currently, we allow that to happen. We give the user the control to perform those actions, right? To say, I'm putting a Porsche over there, a Mercedes over there, and then a not so nice car over there, or a conflicting car with those kinds of cars. And as a result, the system will try to do that, and it may not come up with a very clean axis. This raises interesting opportunities to look at things like confirmation bias and other kinds of bias that exist, and how we might combat that. Or maybe that exemplifies the path of going down two different hypotheses. So the system might understand that and start to split the analytic path that a system goes down, and so on. So there are interesting opportunities for that. But from students, over on this side. Any students have any questions? This is like the faculty side of the... Yes?
Are any tools available for us to play with online?
Yes, so that third one that I showed with the cars that is available, I'll actually go ahead and go back and show you the URL. I have no idea what happens if a lot of you in this class or in this room right now go to that website, but you can try it. There it is. It's not a very short URL, but it is up there. And that car data set is preloaded and everything. And it's a fun one to play with because I think most of you are familiar, at least to some extent, with cars. And so having the chance to play with them is kind of neat, right? We actually put a use case in the paper and the video for this paper that showed how searching for cars that you think you might want based on all-wheel drive and other kinds of things reveal interesting alternatives that you may have not considered. And that was sort of one of the interesting and novel contributions of this work, is to think about how does one start to discover attributes of your data, right? Like, is it a wagon or not? Is it a hatchback or not? That you may not know ahead of time. And so this kind of tool not only helps you weigh those, right? Like, how much do I care about fuel efficiency versus horsepower, but also helps you discover them, because given your data set, you may have not been aware of those to begin with. Yes?
So visualization is primarily known as hypothesis generating rather than hypothesis testing. How do you see this, how could you, once you start moving these dots around and you see interesting patterns, how do you extract from that maybe a hypothesis? How do you formulate it maybe? So you, in some ways, you do this with the linear combinations. This is what you like. But if it's less than preference data, can you generate some sort of automatic means of creating hypotheses?
Yeah, so, right. So currently the hypothesis is quantified using this linear combination of attributes. They have weights on them, so on and so forth. However, the cognitive formulation of a hypothesis may be far more complex than that. And currently that is somewhat implicit or transitive in the way that our systems are designed, and basically saying we help people formulate and test their hypotheses, where the cognitive representation of a hypothesis is perhaps more complex than this linear combination of weights. And that opens up the space to consider other kinds of ways that we actually quantify and help people represent computationally a hypothesis or competing hypotheses. And other kinds of structures to help people reason about their data.
Else? Well, if there are no more questions, let's thank Alex again.
Yeah, sure. Thanks.